sorry, 7, 8. And we've got power series. So yesterday we introduced Taylor polynomials, these approximating polynomials, where if I'm given some function, I want to find a polynomial that's close to it. And we can specify how many degrees of the polynomial we want. I think yesterday we did a degree 3 polynomial. Today we're going to kind of approach that from sort of the opposite side. Well, what if given a function, in terms of a series, so can we define a function in terms of a series? Or moreover, if we are given a function, and let's say of the form so it's the sum of constants times powers of x. So in some sense, all this is it's kind of asking the question, well, how big of a degree polynomial can we have? Can I define a function as an infinite degree polynomial? And how do we make sense of that? So we're kind of, this is just a generic formula. We've got essentially an infinite degree polynomial, right? N equals 1 is my first time. Actually here, sorry. We want to start at n equals 0 here because we're starting with a x to the 0, just a constant term, plus some linear term, plus a quadratic term, and it's just going to keep going. Where our coefficients, we might have to come up with some sort of formula for, or maybe we're given a formula for the coefficients, of how the coefficients change as I'm looking at increasing powers of x. And so our question is when is this defined? In other words, can I plug in values of x for which this series overall will converge and give me a number? So at least sort of the first thing to note if I have a function defined in such ways, what happens if I plug in x equals 0? We just get well, if I plug in 0 for x, what's going to happen if I plug in 0 for all the x's here? We are just left with a constant term. So 0 is always in the domain of f of x. In other words, okay, well, I can actually define functions like this. There are some values of x that will always work. Namely, I can always plug in 0. And so now our question kind of becomes, well, is that the only value? Is this function only defined at one point? Is 0 the only value we can plug in? Or could there possibly be more values for which this function makes sense, for which it will be defined for? So now our question is how to find the domain. And what we're going to do is we are going to use the ratio test. So you can kind of think that if my x's, this is just, if I kind of ignore the cn's, it's just a sum of x to the n. So if I pick x is equal to 1/2, well, that's just a sum of 1/2 to the n, which is a geometric series, right? These power series, in some senses, they're infinite polynomials for whatever value I plug in, at least because I'm adding up successive powers of whatever value of x, it looks a priori similar to a geometric series. And our geometric series is essentially the sort of key foundation behind these ratio tests. That's really what a ratio test gives us. It tells us, is the series roughly geometric, and what is the coefficient that we're multiplying by every time. So for whatever value of x we plug in here, since it's going to be kind of like a geometric series, well, we also have to consider the fact of this CNs. So we can use the ratio test to get information about our CNs to determine, well, which values of x will be compatible with the rate of growth or rate of decay, so to speak, of our constant coefficients. So hopefully that kind of abstractly makes sense. Let's start off with an example. Let's just say I have a function and I'm defining it by n x to the n. So I didn't start at n equals 0 because even if we did, it would be 0 times a constant. So it would just be 0. So what is this series? This series is just x plus x squared, 2x squared, plus 3x3, plus 4x to the fourth, plus et cetera, et cetera. Looks like a typical polynomial. Our coefficients are just the same as the power, but I want to add up infinity powers of this. Well, like adding up infinity numbers is tricky, as we've seen, and so we want to know, well, what numbers of x can I plug in that will add up infinitely many? So by the ratio test, so our individual terms are just going to be nx to the n of this series. So nothing too new, except now instead of just, having n's, I now have this sort of second variable, this variable of x in for my terms of a series. And my an plus 1 is going to be n plus 1 times x to the n plus 1. And then so by our ratio test, the series will converge when the ratio of the terms is less than 1. The ratio of the absolute value of the terms is less than 1. So what does this say? This means we want the limit as n goes to infinity of n plus 1 x to the n plus 1 over n x to the n and we want that to be less than 1. And so we can do our algebra and simplify this again. Nicely enough, the powers of x are going to simplify. We'll just get x. And keep in mind, we're taking the limit as our n goes to infinity. So we're not taking x going to infinity. So what is this limit? Well, as n goes to infinity, this coefficient just becomes 1, and there's no other n's, so x is going to maintain and just be x. So as I compute this limit for n's, we're just left with absolute value of x is less than 1. In other words, our logical statements say that this series will converge when absolute value of x is less than 1. In other words, the series converges for x in between -1 and 1. So this is called the radius of convergence. Or possibly the domain of convergence. It is essentially the domain of our function. Namely, if I have this function, f of x, defined by this fancy power series, I can only plug in values of x between -1 and 1. So we've seen functions kind of like this. Think of like your arc trig functions, your inverse trig functions, like arc sine. You can only plug in values between -1 to 1 for arc sine, right? Certain functions have restricted domains. And this function, just by the way we're trying to define it, we have to restrict the domain. The biggest domain in some sense that we could possibly have is only -1 to 1. We can't include other values of x because it won't make sense as a function. Does that make sense? Any questions on that? So this is our basics behind power series. We now have a tool to develop a much broader range of functions, right? We've got all our trig, inverse trig, natural logs, exponents, and now we have this new way of defining functions by potentially adding up an infinite polynomial. So these are called our power series because they're essentially just adding up powers of x. Let's do one more example, and then we'll try to do this homework problem real quick. So we want to find the radius of convergence of, let's give it a name. Let's call this function g of x, and let's define it with an exponential now. What is this function? So if it helps, always write out a few terms. And actually, let's change it. Let's start at n equals 0. So for the most part, all these power series should start at n equals 0, just to include a constant term. So what is that? When n is 0, it's going to be 0 factorial times x to the 0 plus 1 factorial x to the 1 plus 2 factorial x to the 2 plus 3 factorial x to the 3. And always remember 0 factorial is just 1. It's kind of, there's like combinatorial reasons primarily for why it's 1. So we'll have 1 plus 1x plus 2x squared plus 3 factorial is 6x cubed. 4 factorial is 24, x to the 4th. And we want to keep going. Infinity degree polynomial. So these coefficients themselves are getting to be really, really big numbers. And so we want to ask ourselves, what values of x could I plug in here for this to make sense? And so we do the ratio test again. Our an is just going to be n factorial x to the n plus 1. Our an plus 1 is n plus 1 factorial x to the n plus 1. And by our ratio test, we want the limit as n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial x to the n plus 1, excuse me, x to the n. We need that to be less than 1. And with a lot of these power series, the x's will always simplify nicely. We will see some more harder examples eventually. Sometimes there could be a 2n or 2n plus 1 or something in there. N plus 1 divided by n plus 1 factorial divided by n factorial simplifies to just n plus 1, right? Because I factor out that n plus 1 from the numerator, and then I can cancel out those factorials. And now we get something a little weird. So we need the limit as n goes to infinity of n plus 1 x to be less than 1. Well, what's happening when n goes to infinity? This term's going to go to infinity, right? It's just n plus 1. So in some sense, what we want to do is solve for x. So another way we can sort of arrive at this, if I can't compute the limit, you can kind of think of this as an inequality we've got set up. So we've got the limit as n goes to infinity. This is absolute value of n plus 1 times the absolute value of x. X could potentially be negative, so we want to keep those absolute values there. Of course, we can get rid of them now on the n plus 1 since n is going to positive infinity.
How did you get rid of the x to the n and turn it just into x?
Whoops, this should have just been x here because it was n plus 1 over n.
Okay, yeah.
I wrote that exponent wrong there in the previous line. So what we need, if I move the n's to the other side, it says that the absolute value of x needs to be less than 1 divided by the limit as n goes to infinity of n plus 1. So what do we get? This is 0. This is actually kind of a weird vacuous statement at the moment because by the ratio test, we want strictly less than 1. But when it's equal to 1, it's inconclusive, right? And equal to 1 could go either way. And unfortunately, now I have a number whose absolute value needs to be strictly less than 0, which is not possible. So, of course, the only thing to do here is to check our base case, essentially that we kind of started off. If x is equal to 0, what do we get? We get the limit as n goes to infinity of n plus 1 times 0. And because that 0 is hard-coded 0, it's not a function going to 0 or anything like that, this limit will always be 0, which is less than 1. So this is our only value that works. We say in this case that the radius of convergence is 0. In other words, our domain is just 1 point. The only value of x that will work for this type of series is x equals 0. So it's kind of a kind of a bad way to represent a function. It's only a function that's defined at x equals 0, and it only takes one value at that one point. No other x's will work. Any questions on that? So we'll pick up with this tomorrow with a slight generalization. So far, all of these power series, we can consider them series centered at 0. We can shift it a little bit, and it's going to change the interval of convergence or the domain of convergence. If I define a function like something like x minus 3 to the n over, let's say, n squared. Let's say n equals 1 to infinity. Now, since I don't have just x's to the n's, I have these quantities, x minus 3 to the n. So we'll have a little bit more work to do in solving these intervals of convergence. The radius of convergence is one thing. It's kind of the radius for the values that will converge. But eventually what we will find is, so here's x equals 3. It's essentially just, we will find some interval, some radius for which our domain will be defined about x equals 3. So our sort of domain of convergence might be offset from 0 a little bit. So for the last sort of 8 minutes or so, let's take a look at one of the homework problems that you guys have. And it's kind of related to well, it is the function essentially that we used yesterday. And you kind of want to think about these, in some sense, get used to these approximating polynomials. The nice thing about using these approximation polynomials is that they can give you a little bit better sense of the function and how it behaves without having to, like, hopefully at least do too many derivatives or anything like that. So we have show that if we have some series that converges, and moreover the terms are positive, so it's a positive series, terms are decreasing fast enough that it converges, then this series converges. Sorry, k equals 1 to infinity. The conclusion of this one, it's actually, I mean, it's pretty easy. It's just kind of getting there. It's kind of like, well, what do I do? How do I compare these two things? So if we were to write these as functions, right, we want to think of series as some sort of function. In some sense, we have this comparison. If my AK was modeled by some function f of x, I want to compare some function versus natural log of 1 plus that function. And let's actually start with perhaps maybe the easiest function other than a constant function. Let's start with just y equals x. So I want to compare these two functions. And we did a little bit of this yesterday. We actually kind of analyzed, well, if I wanted to model this function by a polynomial, a degree 3 polynomial, we came up with the appropriate coefficients. And well, what do we know about these two values? One thing to note is that our k starts at 1. So we only have to consider our domain from 1 to infinity. So x equals 1 to infinity. And let's check. So at, well, just to pick a simpler value, I'm going to pick 0. Why do I want to pick 0? Ultimately, I want to analyze, what's going on from 1 to infinity. I'm picking 0 because you should have at least some familiarity with natural logs and of course, polynomials. 0 is an easy number to plug in. If I plug in 0 here, what do we get? We get natural log of 1, which is 0, which is also equal to this function evaluated at x equals 0. So I know that these two functions are equal at a point. We saw this on the graph yesterday when we were approximating these polynomials, or approximating natural log of 1 plus x by a polynomial. Whoops, I didn't shift that, did I? So what should our graph look like? So natural log of 1 plus x shifted to the left one of a normal natural log function. And it should go through the origin. It's going to be something like that. And then our x, we found the tangent line to this polynomial. And we actually found this y equals x to be the tangent line. And then we further tried to do a quadratic and a cubic. And well, what do we notice about the two functions? That this guy is always less than the tangent line. So we can do some basic kind of Calc 1 analysis to prove that, just to kind of show all of our work for this instead of just drawing a picture and saying this is what it is. Excuse me. So we have this intuition. What's going on? Well, natural log should grow a lot more slowly than y equals x. Namely, if I take a derivative of those two functions, what are we comparing? We are comparing 1 over 1 plus x with a constant rate of change of 1. Which one's less? Since x is bigger than 1, on 1 to infinity, of course, we could even say on 0 to infinity. 1 to infinity is ultimately the domain we want to care about. We kind of added in this extra value to get a point of comparison for, do you guys remember the racetrack principle? So let's actually give our functions names so we can make a good statement on this. So let's just say our f of x is 1 plus natural log 1 plus x, and our g of x is x. What did we just showed? We showed that at 0, these two functions match. And we showed that the derivative of the natural log function is always less than the derivative of my polynomial function. Beyond that point. So they match at 0, but then beyond that, I know the derivative of f is less than the derivative g. Thus, natural log of 1 plus x is less than x. On 0 to infinity. Or even, I guess we could say 1 to infinity to get this strictly less than. What does this mean? Let's go back to our original problem. We had a little bit more going on here. I had this sequence of numbers, and I know that I can at least add up all these sequence of numbers. And we want to show that the natural log of 1 plus that sequence will converge. So by this statement, that for any number, that I plug in for all AK, since AK is greater than 0. Right? What was our condition on our sequence? It was specifically positive numbers that I'm plugging in. And what did we just show here? I showed that for any positive number, that number itself is always going to be bigger than the natural log of 1 plus that number. So really all we're kind of thinking about is, well, these AKs are just numbers. These X's are just numbers. So we get this statement as well. Natural log of 1 plus some number, however it's defined, is going to be less than that number as long as those numbers themselves I'm plugging in are bigger than 0. And so we get a direct comparison. And I know that because AK is positive, this is going to be bigger than natural log of 1. And so I know that this guy itself is also bigger than 0. And so because this guy converges as the information that we're given, this guy converges. Any questions on that? So sorry, I'm running a few minutes late on that.
Sort of, but like if people want to leave, that's fine. I just have work tonight, so I can't make office hours.
Sure. So let me go ahead and stop the video. If you guys want to stick around